In the last video, we saw that it's possible to use a table of values correctly and be misled by it and make the wrong guess. I don't remember if I actually stated our final conclusion, which was that the limit as x goes to 0 of sine pi over x does not exist. That was the correct answer to that question. What I want to do now is look at a graph instead. As a general rule, graphs are going to be more helpful than tables because graphs can capture infinitely many points, whereas a table of values will only capture finite points. However, even with graphs, we're going to be dependent on having an accurate graph. I'm going to tell you here that on this graph of f of x, if it looks like a point or a hole has integer coordinates, it does. Without that information, I wouldn't know that this point, for example, was exactly at -1, 2. But if I tell you this is meant to be that points that look like they have integer coordinates and holes that look like they have integer coordinates actually do. Okay? With that information, I know that this is a precise and accurate graph. Do be careful with graphs that you generate using a graphing calculator, whether it's an actual handheld calculator or something like Desmos online. With those, you're sort of eyeballing about where the points are. You don't necessarily know exactly where they are. So graphs can be limited as well. We're going to find that algebra is our best way of evaluating limits precisely. But if we do have a graph that we know is accurate, then that can allow us to know for sure what the limit of a function is. If we're sort of eyeballing and trying to read the graph to the best of our ability, we're getting an estimate. Okay. Here we're going to be able to use this with the additional information I gave us to actually evaluate these 7 limits, or to say that they don't exist. So let's just work our way across. I want to look at the limit as x approaches -3 of f of x. So here's -3. Now, of course, x is -3 anywhere on this vertical line at -3. So I kind of want to look here and above and below to see where is the graph. In this case, it's actually right there. It looks like the graph passes through a point here at -3, 0. And as we follow the graph getting closer and closer to -3, coming in from the left, coming in from the right, I expect there to be a point right where it is. And so it turns out that the limit here is just 0. It is the function value here because nothing weird happened. I got exactly what I expected. So here, the answer to what's the limit and the answer to what's the y value of the point is exactly the same. All right, let's look at the limit as we approach -2. So -2 is here. Of course, I'm going to look above and below, and I see that the graph is up here. It's above the x-axis here. Now, approaching -2, coming in from the left, I'm kind of expecting there to be a point there. There isn't, there's a hole, but I expect there to be a point up here at a height of 2. Okay. Oh, I probably should have labeled my y-axis. This is 1, 2, 3, -1, -2, etc. Okay. Coming in from the right, I'm also expecting there to be a point there. There isn't, but that's what I'm expecting, so I would say that the limit is 2. That's because the value of the hole here, and I can label it the same way I would label a point, the hole is exactly at -2, 2. All right. Let's take a look at the limit as we approach -1. Okay. So, approaching -1, coming in from the left, kind of expect there to be a point there. There isn't, but I expect there to be a point at -1, 1. Coming in from the right, I expect the same thing. Now, there does happen to be a point whose x value is -1. I don't care. That's not relevant to the limit. That's weird. That's surprising. I didn't expect there to be a point there. The limit is telling me where I expected there to be a point. And I expected there to be a point right here with a y value of 1. Okay. I will just point out, at both this location and this location, the hole is where we would have sort of a sharp corner. Here, I'm taking the limit of f. I'm saying, what do the y values of f approach? I'm not taking the limit of the slopes of secant lines. Secant lines would have an abrupt change at those places. But here I'm just taking the limit of f. What are the y values of f getting close to? All right, if I look at the limit as x approaches 0, when x is 0, we're just on the y-axis, coming in from the left, coming in from the right. I expect there to be a point right here at 0, 1. There is a point at 0, 1. Doesn't matter. That's what I expect, and that's what the limit is telling me. All right, what happens as we approach 1? So 1, x is 1 along this vertical line here. So approaching that from the left, I'm expecting there to be a point right here, and there is. Coming in from the right, I'm expecting there to be a point down here. There isn't. But what's important here is that my expectations were different. I expect a y value of 1 coming from the left. I expect a y value of -1 coming from the right. 1 and -1 are different answers. And the limit, if it exists, has to be unique. So we would say this does not exist. All right. Now at 2, as we approach 2, this is kind of interesting because I've got a vertical asymptote at 2. So I can see, coming in from the left, we just keep going infinitely far down. And coming in from the right, we're going infinitely far down. Might be tempting to say that the limit is therefore negative infinity, because my y values do go off towards negative infinity. Based on the definition we've given of the limit so far, we can't say that. So far, we have defined a limit to be the number, if it exists, that a function gets close to. Negative infinity is not a number. So based on the definition we have so far, we would have to say it does not exist, and this one is just because negative infinity is not a real number. Now here, I can certainly describe the behavior of the function. It's going infinitely far down. So we will, in a moment, expand our definition of limit to be able to describe that pattern. But based on what we've said so far, that limit does not exist as a finite number. And sometimes when we're working with limits, we're going to care about getting finite numbers. Sometimes we're going to just care about describing the behavior of the function. Okay. All right, let's take a look at the limit as x approaches 3. So x would be 3 along this grid line here. Coming in from the left, I'm expecting a point with a y value of -1. Coming in from the right, I'm expecting a point with a y value of 0. -1 and 0 are not the same, so I'm going to say does not exist. Notice, here and here, we had the same sort of thing going on. We had that coming in from the left and coming in from the right, we expected different values. Here, we jumped from a point to a hole. Here, we also jumped. We jumped from a hole to a hole, and there happened to be a point somewhere else. Really doesn't matter. If you're jumping like that, so that you're expecting different values from different sides, the limit will not exist. Now, what's interesting is at this place, and at this place, and at this place where the limit doesn't exist, we can still describe the behavior of the function. So this is a little bit different from the limit not existing in the example that we just did, where we had this erratic behavior and we had these wild oscillations going on as we got closer and closer to zero. So we will, as we move forward, define some additional limits that will allow us to describe the patterns that we actually do see here. But right now, if we're talking about a two-sided limit as a unique number that we expect, the limit doesn't exist for any of these. In this case, because negative infinity is not a number, and in these two cases, because the numbers that we are expecting are not unique. Okay,